Hello class, today we're going to talk about 3.5 reciprocal trig functions. So we have to make a distinction. What does a reciprocal mean? The word reciprocal means to flip a fraction, okay? And that comes from, if you remember, that everything is a fraction. So even if you see a number, for example, y equals 3, 3 is a fraction, which is basically 3 over 1. So when we take the reciprocal, we're flipping the fraction, and so y equals 1/3. So this comes in handy when we're talking about trig ratios, because when we think about when is it possible for our trig function sine, cosine, tan to be reciprocal. So when can we actually take the reciprocal? And there are special circumstances. In the warm-up, they've discovered that there are specific reciprocals that happen. For example, there are only two numbers that are the same, or called self-reciprocals, meaning that when you take the reciprocal, when you flip the fraction, it is the exact same value. And that happens, for example, with the positive 1. Because positive 1 as a fraction is 1 over 1. So when you take the reciprocal, it stays 1 over 1, which is again just equal to 1. So 1 is a self-reciprocal. There is another one, and that is negative 1. So y equals negative 1, which is negative 1 over 1. When you flip it, yes, because a negative becomes top or bottom, it does not matter. It still stays as negative 1. So 1s are special in the fact that they are self-reciprocating, so that no matter what you do when you take the reciprocal, it stays the same value. But that's different in other cases, like we saw with 3 and 1/3. So now let's go into the idea of the word reciprocal again. The word reciprocal is very different than the word inverses. Reciprocal, as we said, is when you take the fraction of, so for example, if we take sine, now we take an actual function, sine of x or sine of theta is a fraction. It's over 1. Everything is a fraction. It's just over 1. So when we take the reciprocal of it, it becomes 1 over sine of theta, okay? Which is, as we know, the reciprocal trig function of cosecant theta. And that's why we call these reciprocal trig functions. This is different than if we were talking about an inverse. An inverse undoes what it does, what you would normally do. So for example, when we used to do 3x equals 9, in order to solve this equation, we would undo what's happening on the left side. So typically this is a multiplication. And so to undo it, we would divide by 3 in order to solve, right? So this is an inverse. In trig, that happens when we talk about sine of theta equals a ratio, for example. So let's go 1/2. So an inverse, what we do is we get rid of sine by doing the inverse of sine. And that eliminates sine from the left side. But what you do to one side, you have to do to the other. And that's why, in order to figure out theta, we always took the sine inverse in order to figure out what the actual theta was. So that's an inverse. This is a reciprocal. And today we're just talking about reciprocals. Okay? They're not the same. All right, so here is an example of what reciprocals look like. The graph of sine is this original purple graph here. Okay, so what you see, here's our axes. Here is our y-axis here. And there is our independent axis here, which is theta in this case, in radian mode. And so sine graph, as we know, goes from the midline to the max, down to midline, down to min, and then repeats the cycle. Cosecant is the inverse. So when we discover a cosecant, we are basically taking the inverse. Remember, cosecant of theta is equal to 1 over sine of theta. So it's the reciprocal of whatever the ratio was. So for example, we have a dot here. This value here is telling me that sine of pi over 2 is equal to 1. Well, when we take the reciprocal of that to get the cosecant of pi over 2, we're flipping 1 over 1, which becomes and stays 1. So that's why we were talking about that self-reciprocating. That point stays the same. But that's not always the case. For example, here, if we look at maybe a half, okay? So when if sine of theta is equal to a half, cosecant of theta will equal 2. So that value is now all the way up here. Okay, and so same over here, a half over here again will be 2. And so if you take the reciprocal of every value along the sine graph here, you get this curvature that is a cosecant. But then you're saying, okay, great, I understand this curve. Well, what happens here? Why are there asymptotes? Well, the asymptotes happen because at these points here, this is sine of theta is equal to 0, right? That's what happens when it crosses the x-axis. Well, if I take the reciprocal of that, cosecant theta would be therefore 0 is a number. You can turn into a fraction. It's 0 over 1. So when you take the cosecant of that, that becomes 1 over 0, which does not work. That's an undefined value. And therefore, we have the asymptotes, which creates our asymptotes. All right, so every time you see the sign being 0, so here, 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 and here, you have asymptotes. Okay, so that's why we have the curvature and asymptote at the 0 of sine. Then we have another curvature, and this curvature is downwards because of the values. These were negative 1, right? So it stays negative 1. We have negative 1/2, which becomes negative 2 over 1. Okay, and the same thing over here. We have negative 1/2, and over here it would be negative 2 over 1. And so you have a curvature upwards from the sine, you have an asymptote, you have a curvature downwards, you have an asymptote, and then you have another curvature upwards. And that's how we get our cosecant graph. So our cosecant graph is made up of all these curvatures away from sine with those asymptotes in between. Okay, so once we know how to draw our sine graph, now to draw the cosecant, we just take those values and we kind of reciprocate them and put the asymptotes in. So that's sine and cosecant. What about, so when we answer the question, the graph of cosecant x has asymptotes when our sine of theta, or x, interchangeable, is equal to 0. Okay, that happens because when we do the cosecant of the same value, we can't go 1 over 0, which is therefore undefined, which is why we have those asymptotes. Okay, so vertical asymptotes. All right, where do they intersect? They intersect at those self-reciprocating numbers, which is when sine of x is equal to 1, or when sine of x is equal to negative 1. So all of those max and min points. Okay, so all of those max and min points are the same dots. So we have, again, anytime you see the sine graph going like this, that maximum point here, oops, I should make it intersect, will always be the same. So they have that shared point, okay? When sine is positive and increasing, cosecant is positive but decreasing. Okay, and that happens if you think about the fraction values, right? So when you have numbers like positive increasing, so when sine is having the values of 1, 2, 3, 4, for example, the cosecant would therefore be 1 over 1, which stays 1, 1/2, 1/3, 1/4, which is a decreasing number, right? Think of those fractions, those are decreasing. Okay, and that's sine. Well, the same pattern actually happens for cosine, because sine and cosine are just shifted graphs from each other, but the values when you reciprocate them are doing the exact same thing. So as you can see, cosecant starts from the y-axis and does the loop, versus cosecant, cosine and secant, it happens across the y-axis. So here is the cosine graph. There's your y-axis, which is your middle of your graph here. But then the the secant graph, which is for cosine, is now doing the same pattern of the loops, the parabolas. But they also have the asymptotes again, and the asymptotes happen again whenever cosine is equal to zeros. Okay, so whenever cosine is equal to 0, we have our vertical asymptotes again. Okay, so same pattern, same features that we saw up here are happening with cosine and secant. All right, what about tangent? All right, so tangent graph, if you recall, the tangent graph looks like this one, the purple one here. So tangent will be my purple, and it looks like that. It goes across the y-axis and does kind of like a cubic graph, right? Like it has that cubic look to it, and it has the asymptotes. It has the specific asymptotes at pi over 2 and negative pi over 2. So here are all my tangent graphs here. And as I mentioned, it has these asymptotes here, okay, at the pi over 2 intervals. Okay. But the cotangent, which is what the new reciprocal of tangent, it is the flipped versions, but it's not flipped from the exact same spot, because again, if we look at the points here, and we say tan of x is equal to 0, that reciprocal produces an asymptote again. And so we will end up having an asymptote of here. Wherever you see tan of 0 being, tan of x being 0, that's going to be a vertical asymptote for cotangent. Again, it happens here, so that becomes an asymptote. Again, it happens here, so that becomes an asymptote, and so forth. So every time you see tan of x becoming a 0, that's when the asymptotes happen, okay? Oh, no, wrong one, this one here. And then the graph, again, so whenever you see tan of x is positive and increasing, just like the numbers I was talking about before, cotangent of x will be positive, but it will be decreasing. Okay, because again, whenever you have the numbers 1, 2, 3, 4, your reciprocal will end up being 1, 1/2, 1/3, 1/4, which is getting smaller. Okay, so that's why you see when here it's going decreasing at the positive tangent when tangent's increasing, and then when it's negative, it is decreasing. Okay. All right, because when you throw the negatives in here, you're going to get, again, smaller numbers. Or, sorry, bigger numbers. Because it goes from -1 to -1/2 to -1/3. So that's actually increasing if you do the negative version. Why would I not give this graph full communication marks? Well, there's lots of things going on with this graph. You don't have the vertical asymptotes labeled. You don't have the y and the x labeled here. So lots of things going on. So make sure that you always have full communication marks. Okay. All right. We are going to talk about just how do we answer questions, and I think I'm going to save that for the next video. All right.